Nobel Prize-winning physicist Adam Riess has spent years studying what James Webb and other telescopes are revealing about the universe. His conclusion: this isn't our universe. Because the deeper Webb looked into cosmic history, the less the universe began to behave the way scientists expected. James Webb is detecting galaxies that look far too developed for how early they appear in the universe. Some already seem to contain enormous amounts of mass, less than 500 million years after the Big Bang. According to current ideas about how galaxies form, that should take much longer. And instead of clearing up the problem, Webb has made it harder to ignore. The telescope also confirmed another growing conflict involving the expansion of the universe. For years, cosmology seemed unusually stable. Scientists had a picture that explained the expanding universe, the faint afterglow of the Big Bang, and the way galaxies spread across space with impressive accuracy. It was not perfect, but it was good enough that many researchers thought the main structure was already there. Then Webb began looking into the part of cosmic history that no telescope had ever seen this clearly before. Not nearby galaxies, not familiar spiral arms, the first few 100 million years. That is where the problem started becoming visible. One major survey behind these discoveries is called JADIS. It uses Webb's infrared instruments to search for some of the earliest galaxies ever detected. Infrared light matters because the universe has been expanding for billions of years. Light from very distant galaxies gets stretched on its way to us, shifting into wavelengths Webb was built to see. That is how scientists found objects like JADE's GSZ14-0, a galaxy so distant that we see it less than 300 million years after the Big Bang. The universe was still young. There had not been much time for stars to form, die, spread heavier elements, and build larger structures, and yet this galaxy already appeared bright, extended, and chemically active. Because heavy elements do not appear immediately after the Big Bang. They are created inside stars, then pushed into space when those stars explode or shed material. So when Webb sees signs of chemical activity this early, scientists have to explain where that earlier generation of stars came from. It is a little like finding a fully built city before the roads leading to it even exist. One unusual galaxy would be easier to explain. Astronomy has outliers. Sometimes distance estimates change. Sometimes brightness is misunderstood. Sometimes a galaxy turns out to be boosted by something else, like dust, black holes, or a hidden burst of star formation. At first, many scientists assumed that would happen here too. But Webb did not find just one strange object. It kept finding galaxies that looked brighter, larger, or more mature than expected. Some may still turn out to be less massive after better measurements. Some may be powered partly by active black holes instead of ordinary stars. That matters. But the larger issue did not disappear. The early universe looked far more active than many scientists expected. Then another problem returned: the expansion rate of the universe. This issue is known as the Hubble tension, and it started before Webb launched. One way to measure expansion begins with the early universe. Scientists study the cosmic microwave background, the faint radiation left behind after the Big Bang, measured by missions like Planck. From that ancient light, they calculate how fast the universe should be expanding today. Another method starts much closer to us. Astronomers measure Cepheid variable stars, whose pulsing light helps reveal distance. Then they connect those distances to Type 1a supernovae, exploding stars bright enough to be seen across enormous stretches of space. Step by step, they build what is known as the cosmic distance ladder. The idea sounds simple. Measure nearby distances first, then use those measurements to reach farther out, and then farther again. But the final number did not match the number from the early universe. For years, scientists assumed the disagreement probably came from measurement error. Maybe Hubble's images were too crowded. Maybe dust was affecting the measurements. Maybe the Cepheids were not calibrated cleanly enough. That is where Webb became important. Webb can observe these stars in infrared light, where dust becomes less of a problem and crowded regions become easier to separate. If Hubble had been introducing hidden errors, Webb had a chance to reveal them. Instead, Webb confirmed the earlier measurements. The problem remained. But it does mean the easiest explanation became harder to defend. Adam Riess, who leads the SHOES team, has spent years checking this issue repeatedly. His team measures the nearby universe. Planck measured the early universe. Both methods rely on years of observations, and yet the numbers still do not line up cleanly. That is why his statement carried so much attention, not because it sounded dramatic, but because it came after years of trying to remove the obvious sources of error first. And this is where the tensions stop looking isolated. Because Webb's early galaxy observations and the expansion problem are no longer separate curiosities. They are starting to connect. Early galaxies appear too developed. Some early black holes appear too massive. The Hubble tension remains. And another issue, called the S8 tension, suggests matter may not be clumping in space exactly the way expected. None of this means cosmology is collapsing. That is not what most scientists are saying. Most researchers are not arguing that the Big Bang was wrong. They are not saying physics has failed. They are saying something more careful than that. The model works remarkably well in many areas, but some observations no longer fit as cleanly as they once seemed to. There are possible explanations. Maybe the first stars formed more efficiently than expected. Maybe early galaxies grew through short, intense bursts. Maybe black holes made some galaxies appear brighter than they really were. Maybe dark matter behaves differently under early conditions. Some scientists are even exploring whether dark energy may have changed over time. Each explanation helps with part of the problem, but none of them fully ends the discussion. Solving one issue sometimes creates pressure somewhere else, like adjusting one section of a map and realizing the roads no longer connect properly at the edges. That is why scientists are paying such close attention to these observations now. It is not just one strange image. It is a chain of measurements, corrections, new observations, and repeated conflicts that keep pointing back to the same question. What if the universe is not behaving incorrectly? What if the model is only describing the parts scientists understood best? That is a quieter possibility than saying everything is wrong, but it leaves researchers with a much harder question. What if the model was never as complete as they thought? Webb was built to clarify the early universe. Instead, it may be revealing how incomplete our picture of it still is.